The depth is 10. The y bar is 10, 100 plus 50 is 150 minus by 10 divided by 2. Okay. So this is equal to the width 125 times 10 times by 150 minus 10 divided by 2 is equal to 181.25 times 10 to the power 3 millimeter cubed, or 181.25 times 10 to the power minus 6 meter cubed. Okay. So for point A, we know that we have to consider this area. And it's box beam, right? We have as 2Q. Okay. So the shear stress, shear flow at point A is equal to V over I, right? Q, right? And I have to put a 2 down here because it is what? Box beam. Or I introduce it later, okay? So the 2 over here because of box beam. So this is equal to V. We found our V to be 18 times 10 to the power 3. 181.25 times 10 to the power minus 6 divided by I. I'm just going to use the I value. The I value is 125.17. Okay, so this will be equal to 18 power 3 times 181.25 power minus 6 divided by 125.17 power minus 6 is equal to 26.06. Wait. 18 power 3 times 181.25 power minus 6 divided by, I forgot my 2. Divided by 125.17 power minus 6 divided by 2 is equal to 13032. 13.032 times 10 to the power 3, right? And it's Newton per meter. Okay. And you realize that our answer is exactly the same. Okay, theirs is 13, they round it up. Our first moment of area is 181.25. 181.25 times 10 to the power 6 is correct. Now, how about Q at point B? Okay, so again, this is also equal to thin wall analysis. Right? And it's also box beam 2Q. Now, what is the area to consider? Anyone? What is the area to consider? So if you read what we have written, the area of consideration is relative from the what? Terminal. Right? Yeah, the whole of the second shell. Well done. So now your area to consider is this. Right? Relative to the terminal. So the closest terminal, right? Because if we don't have that rule, we thought that we have to take this section. We thought that we have to do up to here. Yes or no? We have to consider here, right? And here. If we don't have that rule, right? And Abika, you're right. It's the whole of the second shelf only. Because we wrote a rule is the area of consideration is from the terminal. Why? At the terminal, Q, right, big Q is equal to 0. At all the terminals, the Q is equal to 0. So it is like your reference point now already, right? So for this case, the Q at point B, so we know that the width is 125. The depth is 10. The Y bar, Okay, so now we have to consider the y bar. So it's 100 plus 10. So it's 110 minus by 10 divided by 2. So this will be equal to 110 minus by 10 divided by 2 times by 10 times by 125 is equal to 131.25 times 10 to the power 3 millimeter cube. Or 131.25 times 10 to the power minus 6 meter cube. So the Q at B now is equal to 18 times 10 to the power 3 multiplied by 131.25 times 10 to the power minus 6 divided by I, which is 125.17 times 10 to the power minus 6, and divided by 2 because it's box beam. So 18 power 3 times 131.25 power minus 6 divided by 125.17 power minus 6 divided by 2 is equal to 9.436 times 10 to the power 3 Newton per meter. Okay, so they got 9.437, and the first moment of area is 131.25. They also got 131.25. Okay, I did not look at their numbers to do it. You guys saw me, right? We have to understand this concept. Why we only take that area. Okay, so this is the thing about this topic is this: two formulas, right? The shear stress is VQ over IT. The shear flow is VQ over I. It's the first moment of area that is going to like hunt you down. Okay, and I was confused for 3 years before. Okay, when I taught this course, I was also confused. Okay, that's where we derived the formula mathematically first. That's where we came up with those rules. Okay, right. What I'm going to do now, I will see is there another annoying. This one is also very interesting. Okay, same concept though. Okay, I want you to have that so-called that confident. Okay, the confident source is very important. Right. So what we're going to do now? Okay, this one is slightly different. Okay, so this is example. I will not do the whole thing. I'll just elaborate the point. Because we still have to obey the rules, the 6 rules that I've written up for you. Okay, so now we are going to determine the shear flow at point A and at point B, and point B is the confusing part. So I'm going to now sketch. Okay, I'm going to do a sketch first. Okay, and we are going to focus at point B. Okay, so 5 5 11. Okay, so this structure look like this. And then there's 2 vertical coming down by 8. Okay. Now my mouse got missing. Then we have point B is 2.5. I'll not take too long for this. Okay. So now the problem comes again. We have our Vy coming from the top. Okay. So I'm going to look at where they found their Y is 3.7. So this is their Y. Okay, so this is the centroid. So it's about this position is the centroid. Okay. So likewise, we design our shear flow. And we realize that this is one terminal. This is another terminal, right? And this is also a terminal, right? And then at this point, this thing will come in. And this is also our terminal, right? So now it gets really, really confused now. Which is the, so at point A, if we look at point A, so this is where they call point A. Point A is easy, right? Point A is the easy peasy part, right? The question is, how about point B, right? Point B, which one do you take, right? So the idea is this, okay? So this is a very unique problem in the sense that it's unique is where you, so now we have two terminals down here. Is it take terminal on the flange or terminal on the web, right? If you look at point B, right, at point B, right, point B is more taking of the terminal of the what? The web. Sorry, of the flange, right? Why at the flange? Because it is the member over here, right? This is the shear flow that the member is carrying at point B. Okay, if the structure is asking you to find at this point down here, right? If this is your point B over here, then it will be at your web. But this is more focused on the flange. So that is why for this case, you take this area over here. And again, it's a box beam where Q, you have Q going on one side and you have Q going on the other side. Okay, so I'm not going to look at the answer. I'm going to find out whether it's our Q going to be the same. Okay, so the first mole of area for point B, right, is equal. So their width, okay, just go look at their width. Their width is going to be 10. The depth is going to be 0.5. And then the Y bar, so we know that from the top, I'm assuming it's from the top, okay, it's 3 point. So from the top come down, it is 3.70946. Okay, so 307,946. So from the bottom is 8 minus 3.70946 is equal to 4.29054. Okay, let me do it again. So no, it's 8 plus 0.5. I can be wrong down here. 8 plus 0.5 minus by 3.70946 is equal to 4.79054. So once I know that, so 4.7, so is 4.79054 minus by 2 plus by 0.5 divided by 2. 2 plus by 0.5 divided by 2. Okay, so this will be equal to 2 plus by 0.5 divided by 2. 4.79054 minus by 2.25 times by 0.5 times by 10 is equal to 12.7027 inches cubed. Okay, so this is our point B, and it's exactly the same. Okay, so you have to understand that concept. Okay, that where the shear flow is, which terminal to pick, not necessarily the closest one. Okay, it depends on where it's attached to. Okay, so B is attached to the flange. No, does not matter to where's the closest terminal, as you can see down here. Okay, Abeka. Yeah, it does not matter. Okay, so it's an interesting problem. That's why I like to pick all this problem up. Okay, but however, if they say point B now is in the web, you take the web. Okay, guys, I will post the homework tomorrow morning, and I'll upload the videos or tonight. Next week you're going to get another quiz. Okay. Now tomorrow you will know whether you will need to do corrections or not. The correction will be done on Tuesday. Sorry. Let me decide when the correction will be yet, because I don't want to miss any lectures. Okay. So if those of you have to do correction, you might need to do it at 7 to 9:30 again, and then watch the lecture on video. Okay. Don't worry too much. Okay. Let me plan first, then let you guys know. Other than that, I'll see you guys next week. Bye.